Welcome, fellow engineers. Today, we're diving into one of the most fundamental concepts in modern AI, vectors. These aren't just abstract mathematical ideas. They are the very building blocks that allow AI systems to understand, reason, and interact with our complex world. By the end of this lesson, you'll not only grasp what vectors are, but also appreciate their immense power in practical AI applications. Our objectives are clear. First, you'll understand how vectors serve as AI's universal language, representing diverse data types. Second, we'll explore the core vector operations that fuel modern AI models, from simple arithmetic to measuring similarity. And finally, you'll gain practical insight into how these operations are leveraged to build real-world systems, like recommendation engines. Let's unlock the intelligence behind AI, one vector at a time. So, what exactly are vectors in an AI context? Forget complex physics. In AI, a vector is simply a list of numbers that represents anything, a word, an image, a user's preferences, or a product feature. Think of it as a unique fingerprint for data. Each number in this list, or dimension, captures a different aspect of the item being described. For example, a user's movie preferences might be a vector like 4.2, 1.1, 5.0, and 2.8, where each number rates their interest in action, romance, sci-fi, and comedy, respectively. Or a word like cat could be represented by a vector like 0.8, 0.2, 0.9, and 0.1, with dimensions for animal, furniture, pet, and vehicle. The brilliance lies in how these numerical representations allow computers to mathematically understand and compare seemingly abstract concepts. It's how AI converts the messy real world into structured, quantifiable data. Once we have data as vectors, we can perform operations that unlock incredible insights. First, we have addition and subtraction. These operations allow us to combine or contrast concepts. A famous example is king minus man plus woman equals approximately queen in word embeddings. It reveals semantic relationships. Next, the dot product is crucial for measuring similarity. If you have two vectors, a higher dot product generally means they are more alike. Imagine comparing two users' movie preferences. A high dot product suggests similar tastes. Finally, magnitude and normalization are about standardizing vectors. Magnitude is the length of a vector, and normalization scales vectors to a uniform length. This is vital because it allows us to compare vectors purely by their direction in space, rather than being influenced by their size or intensity. These operations form the bedrock of how AI systems make decisions based on data relationships. AI systems are constantly asking, how similar is this to that? Vector distance gives us the answer. The cosine similarity, or cosine similarity, is perhaps the most common measure in AI. It returns a value between -1 and 1, where 1 means identical and -1 means completely opposite. Another method is Euclidean distance, which is simply the straight-line distance between 2 points in vector space. These distance metrics are the heart of AI decision-making. You encounter them daily. Search engines convert your query into a vector and find similar document vectors. Recommendation systems find users with similar preference vectors to suggest new content. And image recognition systems convert pixels into feature vectors and then compare them to known object vectors to identify what's in a picture. And large language models use vectors for every word, creating a rich tapestry of relationships through vector math. Let's put this into practice with a simple movie recommendation engine. We define movies by their genre features, like action, romance, or sci-fi, as vectors. When a user provides their preferences also as a vector, our engine calculates the cosine similarity between the user's taste and each movie's features. The movies with the highest similarity scores are then recommended. This simple system demonstrates the core principle behind giants like Netflix and Spotify. In production AI systems, the scale just gets bigger. Large language models use vectors with thousands of dimensions for word meanings, and computer vision systems convert images into complex feature vectors. The underlying math, however, remains exactly what we've covered today. You're now equipped to think like an AI engineer. As a final thought, consider how might you represent a song's attributes as a vector to build a music recommendation system?